In this lesson on classifying chemical reactions, you're going to look at examples and non-examples of each type of reaction to determine the identifying feature of each. We'll begin with synthesis reactions. I'm going to show you some examples of synthesis on the left and some non-examples on the right. These first reactions are pictorial representations where each different colored circle represents a different element, either alone or in a compound. In these next reactions, letters of the alphabet are used to represent generic elements. In addition, we'll look at real chemical equations. Examine the examples and non-examples carefully to find a trait or characteristic that can be used to identify a synthesis reaction because that trait is unique to the synthesis examples. The non-examples won't show this characteristic. Pause the video while you work and restart when you're ready. Hopefully you notice that all the examples only have one substance on the product side of the reaction, so there are no plus signs after the yields arrow. We can demonstrate this using the generic equation of A plus B yields AB, where elements A and B are separate from each other on the reactant side, but are combined into one new substance on the product side. A possible analogy could be Amy and Bob go to the dance, fall madly in love, and become the couple Amy Bob. They started out single, but came together as a couple, similar to creating a compound. Try using the identifying feature to determine which of these reactions are considered synthesis. Pause the video while you work and restart when you're ready. The first reaction lacks a plus sign on the product side, so only one product is created. Therefore, this is a synthesis reaction. The same is true for the second reaction. There's only one substance on the product side, SO3 or sulfur trioxide, so it's also an example of synthesis. The third reaction has two products, KOH or potassium hydroxide and hydrogen or H2. So it can't be synthesis because synthesis can only have one product. Reactions 4 and 5 also have two products. That makes them non-examples because synthesis is a combination reaction producing just one substance. Now let's see if we can find a trait or feature that can be used to identify decomposition reactions. Examine the examples and non-examples carefully to identify a characteristic unique to decomposition. Remember, the non-examples won't show this characteristic. Pause the video while you work and restart when you're ready. Now let's add one more example and non-example. Does the trait you pick still work to identify the decomposition reaction, or do you need to refine it in some way? None of the examples have a plus sign before the yields arrow, so each decomposition reaction has only one reactant. This type of reaction starts with one substance that breaks apart into pieces. This makes sense because the word decompose means to break down. We can demonstrate this using the generic equation of compound XY yields X plus Y, where the plus sign on the product side indicates the products are separate substances not connected or attached to each other anymore. This type of reaction typically requires energy, such as electricity or heat, because energy is needed to break the bonds holding the compounds together so the parts are able to separate from each other. Notice in the examples provided, these compounds can break down into separate elements or break down into smaller compounds. A dance analogy to help remember decomposition could be Xander and Yolanda get in a fight at the dance and break up. So they started together but ended apart. Use the identifying feature or characteristic to determine which of these reactions are considered decomposition. Pause the video while you work and restart when you're ready. The first reaction has two reactants present, indicated by the plus sign on the reactant side. Since decomposition reactions can only have one reactant, this is a non-example. In the second and third reactions, we see there's also a plus sign on the reactant side, so they have more than one reactant. This means they are non-examples. The third and fourth reactions, notice there are no plus signs on the reactant sides That means they are examples of one substance breaking down into pieces or decomposition reactions. Now try to find a trait or characteristic that can be used to identify single replacement reactions, also known as single displacement reactions. Examine the examples and non-examples carefully to identify a characteristic unique to single replacement. Remember, this feature should not appear in any of the non-examples. Pause the video while you work, then restart when you're ready. Hopefully, you noticed all the examples have a single element on one side of the equation and a different single element on the other as one element or ion replaces another in a compound. Those singles are the clue to single replacement. We can demonstrate this using the generic equation of element A reacts with compound BC to produce compound AC and element B. A has replaced B in the compound. This type of reaction usually takes place in aqueous or water solutions because they tend to involve ionic substances held together by strong electrostatic forces in a crystalline lattice structure. The water breaks the crystalline lattice, freeing the ions to rearrange and form new bonds. A dance analogy for single replacement could be Bob and Chloe arrive at the dance as dates, and Chloe dances with Angelo instead of Bob. Angelo was single before, but after they switch places, Bob is single. Determine which of these reactions are considered single replacement. Pause the video while you work and restart when you're ready. In the first reaction, chlorine or Cl2 is single or not combined with other elements. After the reaction on the right side, the iodine or I2 is single. The iodine started in the compound with sodium, but was replaced by chlorine. That makes it a single replacement reaction. In the second reaction, no elements are single. We only see compounds on both sides of the reaction. Without singles, it can't be a single replacement reaction. The third reaction has K as a single element before the reaction, and the molecule containing only hydrogen as a single element after the reaction. This is a single replacement reaction. The fourth reaction does not have any single elements, so it cannot be single replacement. You should now recognize that one as a synthesis reaction. The last reaction has singles, H2 and O2. However, they both appear on the product side. To be single replacement, we need one of the singles to be on the reactant side. This one is a decomposition reaction because there's only one reactant that breaks down into pieces. The fourth reaction you need to be able to recognize is double replacement, also known as double displacement. Examine the examples and non-examples carefully to identify a characteristic. Pause the video while you work and restart when you're ready. All of the double replacement examples have two compounds on each side. The elements or ions, which may include polyatomic ions, switch partners. No elements are single or alone. They are always paired in a compound with at least one other element. We can demonstrate this using the generic equation of compound AB reacts with compound CD to produce compound AD and compound CB. This type of reaction usually takes place in aqueous or water solutions because, again, they tend to involve ionic substances. Dissolving them in water breaks the crystalline lattice holding the ions together so they can rearrange and form new bonds. Pause the video while you think of your own dance analogy for double replacement. Determine which of these reactions are considered double replacement. Pause the video while you work and restart when you're ready. In the first reaction, there's a single element aluminum with a compound. And after the reaction, there's a compound with a single element copper. This is not double replacement because it does not have two compounds on each side. Hopefully you recognize it as a single replacement reaction. The second contains two compounds on each side. Both the hydrogen and the sodium switch places, so it is double replacement. The third reaction does not contain two compounds on each side of the arrow, so it can't be double replacement. This one is a single replacement reaction. The fourth reaction has single elements rather than compounds before the arrow, and only one rather than two compounds after the arrow. Without two compounds on both sides, it can't be double replacement. The last reaction has two compounds on both sides. We can see that the barium and sodium switch places. Each ion starts with a partner and ends with a different partner, so it is a double replacement reaction. The last reaction we'll identify today is a combustion reaction. Examine the examples and the non-examples carefully to identify a characteristic unique to combustion reactions. Pause the video while you work and restart when you're ready. Now let's add one more example and non-example. Does the trait you pick still work to identify combustion, or do you need to refine it in some way? Another word for combustion is burning. In each combustion example, O2 is a reactant. We should remember that things won't burn in the absence of oxygen. So it makes sense that O2 is a reactant because fire won't occur without it. In many examples, a hydrocarbon, or a compound containing carbon and hydrogen, reacts with oxygen to produce carbon dioxide and water. However, in the last example, carbon dioxide and water are not produced. Remember, the law of conservation of matter states atoms cannot be created or destroyed. If none of the reactants contain carbon and hydrogen, then those atoms cannot appear on the product side. So burning metals like magnesium cannot create carbon dioxide and water. While CO2 and water may appear as a product of combustion, the true trait to identify combustion is O2 being a reactant, because all combustion reactions will have that feature. Determine which of these reactions would be considered combustion. Pause the video while you work and restart when you're ready. In the first reaction, O2 is a reactant, which is the identifying feature for a combustion reaction. We also see carbon dioxide and water as products, which are found in many combustion reactions. The second reaction has a reactant containing oxygen, but does not have specifically a standalone O2 as a reactant, which is required in order to be combustion. Having carbon dioxide as a product does not make it a combustion reaction. The third reaction has a compound containing oxygen, but does not have O2 specifically as a standalone reactant, so it cannot be combustion. Having water as a product does not make it a combustion reaction. In the fourth reaction, O2 is a reactant, which is the identifying feature for a combustion reaction. In the last reaction, O2 is a reactant, which is the identifying feature for a combustion reaction. In this case, we don't see CO2 and water as products because lithium, a metal, is burning rather than a hydrocarbon containing carbon and hydrogen. You did a great job. Remember to keep practicing. The more you practice, the better you get at classifying reactions.